recurrence. And this was the smallest one of them. So if we print out all of them, I guess we need as much paper as I stack here. So at least this much paper. We need to print out all these 5 recurrences. So let's stop this. So this was already a non-trivial task to guess all these recurrences. And it's an even more non-trivial task than to handle them and to do some calculation instead. And the rest of the talk will be about that. So 244 megabytes in total.
So
now,
you were printing this even?
I didn't really print it. I don't know. I guess something like that. Yeah, it should be fine. If you use a small font and double page print, double-sided print. Okay, so now let's give an impression how we do this proving of these identities. And we take the first one. We call the first identity was just to prove that the diagonal is always 1. From this definition it is clear, but we have now just guessed some recurrences, so we have no clue whether these recurrences are correct or not, and we have to prove that these recurrences agree with our definition. So we really have to reprove all these statements. We cannot take anything for granted. So how do we prove that C and N is actually 1 for all N? I mean, we used some values for guessing the recurrences. So we computed C and J up to, let's say, 50 or 100. And of course, there it was always 1. But we don't know whether this pattern continues. And so we can use these methods that I have implemented in my package. And in this case, we do the following. We take this annihilating ideal, this ideal of recurrences for this function, and we look for a special element in this ideal, namely which is of this form, that I have always the same shift here. And some coefficients here, which are polynomials. And then I do the following. I substitute J goes to N, and I get a recurrence only in N, the J is gone. And this recurrence gives me the elements on the diagonal. So if I can show, so this will have order 7. If I can show that the first 7 values are 1, and that the recurrence keeps this pattern, that it always produces 1s again, then I have a proof that all of them are 1 recursively by induction. So this was the easy thing. Now it becomes more difficult. So this was the third identity, just to remind you. I have rewritten it a little bit so you may recall that in the matrix entries we had some Kronecker deltas, and if we sum over them, they contribute just a single sum, and so we pull this out. These are these 2 at the beginning, and then we are left with a sum where we have here the remaining part of the A times the original C and J, and I abbreviate and call this expression C prime and J. Doesn't matter so much, just so we have now a problem of the form we want to solve a sum over some function that is described by a holonomic system, a system of recurrences. Okay, how do we do that? First, we have to compute an annihilating ideal, or recurrences for the C prime. So we had, until now, we had only recurrences for C, but this is just a product with something very simple. So there are algorithms for the closure property algorithms which deliver recurrences for C prime. So this is not a big deal. This is quite standard. And then we do the classical telescoping trick. So we find, again, in this ideal of recurrences, we find a special candidate which has this form. So on the left-hand side, we have only shifts in N, and we have coefficients P7. So 7 is like, it turned out to be 7. It need not to be 7 in general. So these are rational functions, or if we cancel denominators, polynomials, which only depend on Q and Q to the N. So there's no J on the left-hand side. And the right-hand side has the nice property that it can be written in this form, that we have something t and j plus 1 minus t and j. And the reason why we need this is because then we want to sum over this whole equation, and then by telescoping, everything on the right hand side goes away by telescoping, and we are left with the left hand side, and this provides then a recurrence for the sum, for the whole sum. There are some details that I do not mention here, like natural boundaries, who is familiar with that, but so this is the principle how it works. Okay, and the t and j is of the form that I don't specify here explicitly. It's a linear combination of some shifts of this function c prime. And the coefficients can be anything, so there can be a q, doesn't matter, because this telescopes away in the end. Yeah, and this procedure is called creative telescoping. We get a recurrence for the sum, and then the rest is rather simple. If you look at the identity, we have the sum plus some extra stuff. So we have to use again closure properties for sums of functions that deliver us a recurrence for the whole left-hand side of the first line, and then we can compare it to the right-hand side, check initial values, do this business, and we get a rigorous proof that this identity is true. But we have to find this certificate relation that allows us to apply creative telescoping. Okay, and the rest of the talk will be dedicated to how we find such a relation. So here I just restate the problem. So this is just like, it turned out in the end that we have 10 of these terms, and these are some arbitrary shifts, just to give an impression how it looks in principle. So the first thing I tried is called the Zeilberger's slow algorithm, and yeah, it's called slow for some reason. I think it was you who introduced this notion, so it's not me, of course it's you. So this consists in brute force eliminating this variable q to the j. We find a recurrence that does not involve q to the j at all, which then trivially can be rewritten in this form with the special property that then also on the right hand side no j occurs. But okay, why not? It does the job. But we do too much. We are allowed to have j here, but we are also eliminated from the right hand side. And that's it, why it's so slow. Yeah, and I tried on this example. These are some numbers that I got in the q equal 1 case. So this is even not the difficult case. So the input, these 5 recurrences, they have then j only, not q to the j, but j in the q equal 1 case, between 24 and 30. And then I started Bruckner basis computation to eliminate this variable. And yeah, so after 48 hours I stopped it because still the smallest relation that was found had still degree 23. And I mean, it grows exponentially. The more we go down, because the coefficients grow, the degree in n will increase dramatically. So there was no hope, and a very rough estimate is this number of days, which is I think it's 1.6 billion days, assuming that the q case will need 100 times longer than the q case, the q equal 1 case, which is a very moderate assumption, and that like in each step we double the effort, which is also a very moderate assumption. So probably we would need much more. So I stopped it after a while. The similar thing for something called Takayama's algorithm, which is usually faster, and we see that we improve already a lot. So we have here now only 52 million days, and I mean if you use parallel computing, maybe if 10 computers, and we have only 5 million days. But still, we would like to improve a little bit. So there's a standard algorithm for solving such problems. This has been invented by Frederick Schistach, and he makes an ansatz. So We know that there must exist such a relation. We don't know the order here, but we can loop over this order until we find